Yeah, so my name's Chris McCormick. I'm a software engineer. I work for a company called CogniMem Technologies. CogniMem is definitely in the machine learning space. That's what we do. So I've been excited to hear about this meetup group in Santa Barbara. And, it's been good meeting Jim, and I'm looking forward to talking to you guys more. I'm actually fairly new to machine learning myself. I joined CogniMem back in February, and since then I've been trying to learn really quickly about this field that I work in. So, I think what I'm gonna be doing in this presentation, I'll show you guys the Kinect demo, and we'll get to play with that afterwards, and then I'm gonna use that kind of as a motivation to explain how our chip works. And the chip implements a couple of machine learning algorithms that I'll walk us through. So maybe by the time we're done, you guys will have a couple more algorithms that you're familiar with. So I'll show the demo. We'll give you a peek of the demo in just a minute here, but a little bit about the company. It's a pretty new company. We were just founded last year, 2011. The main office is actually up north in Folsom, California. It's kind of near Sacramento. And my father, Bruce McCormick, is actually one of the founders of the company. So that's how I'm able to get away with working here remotely in Santa Barbara and all that other things. It's been a sweet gig. So our product is the CM1K pattern recognition chip. The chip was actually created in 2007. It was a collaboration between IBM and one of our founders. So the chip's actually been around a little bit longer than the company. The business is our business is to basically sell this chip and provide development boards and software tools for working with it. So we don't actually create and sell any products or end applications. We just sell the chip, and the idea is that we'll work with customers who will create systems around the chip and create actual products. So there's two algorithms that the chip implements. They're called the k-nearest neighbor and radial-basis function. And those are actually both they're pretty old algorithms. They've been around for a long time. So that our chip it's not contributing any kind of like new revolutionary machine learning algorithm. The value in it is more that it accelerates those two algorithms in a really cool way. And those KNN and RBF I kind of think of them as relatively brute force algorithms. They kind of take a lot of processing power to execute, but they're very simple and effective. But they don't scale well on a traditional processor. So our chip is designed from the ground up to implement these algorithms to be extremely scalable and exploit there's a lot of parallelism inherent to these two algorithms, and the chip takes advantage of that. So I'll go into more detail about those in the chip. So the demo, I'm an applications engineer for the company, so my job is mainly to put together demos and proof of concepts for companies. So one that we've done was this Kinect demo. We did it for a computer vision conference called CVPR. That was in Rhode Island this past June. So let me actually show you guys. I'll show you a little bit about the Kinect, and then show you what we did. I guess any questions? I guess about the company in general before I.
Who's your market?
We're I guess you could say we're trying to figure that out, because there's like the chip is very general purpose in that you can apply those algorithms to a lot of different things. So we're trying to figure out where it makes the most sense to get started. So one area, I think with two of the founders have a lot of background in computer vision, and I think that's kind of what the chip has been designed for. So one space that we're targeting is computer vision applications where you need a really fast response time, and chip because it's a custom ASIC. It runs those algorithms at a much lower power than you could with like a GPU or with a powerful desktop.
I read on the website about the low wattage type stuff, and it was interesting, but it looked like it basically said that it was running at 1/100th the clock speed, and it took about 1/100th of the power to run. So I'm wondering if overall there really is an advantage if it's the same, if you get as much bang for your buck power wise.
So it
is it parallelism? What's special?
Yeah. So I guess what's special is the performance that you get, which if you're using all 1,024 processing elements in the chip, you can easily outperform like a Core i7 processor, and you can do it at a fraction of the power and a fraction of the cost because the chip takes a lot less die space than a full-blown desktop does. So yeah, so I mean it really it wins in every category except for flexibility. It's not the desktop processor is a general purpose. You can program it to do anything you want. But our chip is very fixed function. It's these two algorithms. Got to work within the constraints of what it does.
So just a little follow-up. Have you identified applications where you think you really have an advantage?
Yeah, I think part of it is finding. I think that the chip makes sense in pretty much everything machine vision related, but the trick is finding a space where people are willing to take a risk on a new technology, and where where the chip is just really compelling enough to sell it. And one of the things I think we found is that it's very hard to like consumer electronics, which is kind of one area where we started. Companies like Apple and Microsoft that don't seem to. I guess this is true of Apple in particular. They're not interested in taking a risk on a brand new piece of technology. They kind of let other people try it, and then once it's proven, they take it and polish it, make it really nice. So it's kind of hard to. I think it's hard to get our chip into consumer devices right off the bat. So we have military customers that are working on it, that are working with it, and evaluating it. The other big space that is a really good fit for it is product inspection. So like looking for defects in products on an assembly line. Those are nice problems because they're fairly constrained. You've got what the camera's pointed at is pretty uniform. And the companies that are in that space right now charge a fortune for the systems that they have. So that's one space where we've got a few people working on it. So there's one application that we actually have deployed. It's kind of fun. There's a fishing company in Norway that has these fish sorting machines on all their boats, and I forget whether it's like fishing regulations or what, but they sort the fish. They only want a certain type of fish, and so they're actually using our chip with a camera that this machine like feeds the fish past the camera and it identifies it as either being the right type of fish or the wrong. So fish sorting is our like one success story. So
what about sorting in general?
About what?
Sorting in general would seem that differentiating between products.
Yeah.
So what about facial recognition? The FBI is putting $1 billion into that, and that's everywhere around us, or it's certainly emerging very rapidly.
Mm-hmm. Yeah, I think.
Especially if you can see through ski masks.
Yeah, that's the funny thing about vision. You can always it seems easy to trick it. You just hold something up in front of you. So, let's see, so I was going to show you guys first a little bit about the Microsoft Kinect. It's a really cool toy, if you guys aren't familiar with it. So it's a peripheral for Microsoft's Xbox 360. And what it's got is a, so what it has is a RGB camera plus a infrared depth sensor, and as well as a microphone array that they use for doing like voice recognition stuff. And so what it's able to do is using the depth data, it's able to distinguish human beings, people in the frame, and then track their body movements. So that this green lines you see, that's the Kinect tracking my skeleton. And it's able to track 21 different joints. It's tracking, you can see there's one joint for my hand, one for my wrist, one for my elbow, I have a shoulder joint, head joint. And it works really well, it's incredible. And something that's,
Sorry.
Yeah.
How can we have two pelvic joints?
I'm not entirely sure. One is called the spine, and one is the, I don't know what the bottom is. Yeah, I'm not sure what's distinct about those. I know the spine joint is useful for if you want to recognize a gesture. If you make the joint coordinates relative to the spine, that takes out the player's position from the equation. Kind of normalizes it. Normalizes the joints relative to the spine.
Well, you can raise one hip joint more than the other, so there's.
Yeah, it does look like they can kind of vary relative to each other. So something that's really cool about the Kinect that I think a lot of people don't know is that it actually uses a machine learning algorithm to do this skeleton tracking. So what Microsoft did is they use motion capture equipment to record a number of people doing different poses and actions that I think in particular they tried to like capture motions that you might do in a gesture control video game. And then with that motion capture data, they also simulated some additional data by like making people taller or shorter and heavier and that kind of thing. And so what they ended up with is this database of millions of examples of like voluntary human poses, and what people look like in normal human poses, and with all of their body parts labeled from the motion capture data. And then they actually trained an algorithm called RDF, stands for Random Decision Forests. They trained that on all that motion capture data. So it's not using the sort of traditional software approach of kind of programmatically trying to figure out where the people are. It's actually using machine learning algorithms. So so I think a lot of people aren't familiar with machine learning, and even engineers don't know that much about it. It's kind of an esoteric field. Well, does that really work? Does anybody use that? And this is an amazing example of machine learning in action. Yeah.
So just to be clear, so to get like the final algorithm, they use machine learning, but it's not like learning as each person uses it, right?
No, yeah, it's been pre-trained.
Okay.
Yeah. In fact, they brag in there. They published a paper on it. They say that training the tree, like using some kind of super cluster, took about like 3 days or something like that. So the training was offline, intense. Yeah, and I think the algorithm that they chose lends itself well to. It runs pretty quickly. The trees have a depth of 24 layers, and so it goes through and it tries to classify every pixel on the screen as either belonging to a body part or not. And for each of those pixels, it only has to go through 24 decisions to figure out whether it's part of the body or not. So, it's pretty impressive. So, yeah, if you notice from my skeleton, joint, but then there's no information there about what my fingers are doing, about what kind of hand pose I have. So what we did with our demo was to add that functionality on top of what Kinect joint provides. Let's see. So yeah. So let me actually show you guys our utility. Just do a quick demo of it. Go through how it works a little bit. So we can recognize a lot of different hand poses. We tried a number of them. The two that we kind of really fleshed out and made robust are just an open hand and closed fist. So we're distinguishing between those two, and we're using that to give you control over the mouse. So there's a number of applications we demo with, but I'm just going to show you guys using it with Microsoft Paint. So you wave your hand to take control of it, and then you can click by just doing kind of a quick close and open of your hand. Let's see, and then brush. And so yeah, so this gesture you can use to kind of draw stuff, or drag and drop is another application of it.
Well, that's like a leap, but you can do it from far away.
Yeah, the leap motion is will probably do this a lot better, because the leap is designed to work. You use it, much closer.
Yeah, you're right,
to your
right
body.
there. But here you're doing it from distance.
Yeah, and I think the reason Microsoft hasn't done what we've done here themselves, is that the sensor data just was not quite enough resolution in it really to do that robustly, especially with they want the Kinect to work for everybody, and what we've done doesn't work that well with little kids. To the Kinect, like little kids, like they don't have hands; they just have little stumps. So, but it works well with adults, and that's who usually play with this demo. So it's kind of a cool application of our tech.
You could have a little, like when you go into an amusement park, and if you're not this high, you can't do the ride.
Right.
If your hand isn't this big, you can't play.
Yeah. And I guess they did. We asked them about it, and they did say that they're not doing it, but that doesn't mean third-party game designers are welcome to implement that if they want.
So are you using, in your demo, are you using your chip as part of that demo?
Yeah, so we're using, for the demo, we're using the simulated version of the chip. Because we're only doing 2 hand gestures, it's able to run reasonably quickly in software. So part of the reason we did that is that we wanted, as kind of a fallback, we were interested in convincing Microsoft to use our chip to enhance the Kinect, but they can't. The Xbox is already released. They don't really make changes to it once it's out until they release like another version of it. So we kind of wanted to show them, like, look, you could do this. You could do this in software today, with a limited number of gestures, basically. But really, we'd like to see you guys use our hardware in the next generation Xbox. So that's part of the reason that we did it in software. The other reason is actually just that the development board that we would use for it. I found whenever I've tried it, the connection seems to crash periodically. So when we've set this up at conferences, running it all day long, letting people use it. So the hardware is a little flaky. That doesn't show well. So that's the other reason. Yeah, but you can actually. I've got a couple of our boards with me. Yeah, so this is the development board that we sell for vision applications. It's got one of our chips on it plus a camera. So the code actually, it's using the simulated version. So it's compatible with the hardware. So if I plug it in, it'll run on the hardware. And the other board we've got that actually hoping to kind of expand this demo and use this board. This board has 4 of our chips on it, so it's able to handle a lot more. You can do a lot more gestures with this guy.
How many layers is that board?
You know, I'm a software guy, so how many? I think it's a pretty. How many layers are typically in a board?
2.
2?
No, I don't know. It depends on this, how. It depends.
Yeah. What would you use multiple layers for?
I'm not. I don't have enough knowledge to know. My question, I guess, what's coming up in my mind is, would it be possible to seed kits to distributors like SparkFun or Radiata that would allow hobbyists, not necessarily hobbyists, but semi-pros or professionals who are working on things on the side to come up with more ideas and kind of feed them back to you somehow? I don't know.
Yeah.
Prototype stuff?
Yeah, kind of like, like SparkFun and whatever that, digital electronics, that
Yeah.
people buying kits from, they build various things. I mean, it sounds like, since you're searching for an expanded market, I'm wondering if that would be a kind of a sideband way into learning some new applications.
Crowdsource the finding of the market.
Yeah, in a way, that's what it would be like.
Yeah. And I hope we'll get there eventually. I think right now it's not very geared towards hobbyists. I think we need a big application to give us some funding to invest more in tools as well as do like a cost reduction of our chip. Right now it's running on a older process technology, 130 nanometer, which is like 5 generations back, I think. So on the latest process technology, it can be made much cheaper than it currently costs us. So yeah, it would be easy to do. It's just funding kind of thing. So hopefully eventually the development boards will be able to make really cheap boards and have the manpower to create really good tools that make it easy for hobbyists to pick stuff up.
What is your development board sell for now?
They're pricey in my opinion. This guy's $1,000, and I think this one is $3,000.
In the press release it said, was it $80 if you buy 1,000 of them or something? So like
The chips.
something like that. I mean, there's a
Sounds about right.
huge reduction
Right.
if you buy it bulk, obviously.
Yeah. But if you're a hobbyist, you probably you don't want just the chip. You want the development board, all the peripherals.
What's it like to actually train things? You're talking about, okay, detect different kinds of fish or whatever. I mean, do you click on? Is someone kind of manually training, saying that's what this is the fish in the picture, or what do they have to do? Is there any programming involved?
Yeah.
Like what's the
Supervised learning.
Right. Yeah. Exactly. So far we've been doing supervised learning.
Okay.
So,
okay?
yeah. So for example, I'll actually go through the training process in detail. But for this Kinect demo, part of what we did to get it working was I've collected, I think, about 50,000 images of different people's open hands and closed fists, and I have them organized into directories based on what they are. I manually did that by inspecting the images, and then once you have those images, once your data is labeled, basically, then the training itself is automated. You've written a script basically to pass those images to the training chip.
So that makes sense for you, but what about when a customer wants to use? Are they writing scripts, or are they just like saying, this is a yes, this is a no?
Yeah, I think where we're at. We do have we've got a tool that we provide with the development board on the tripod there. This one's kind of the vision development board. We've got a GUI tool that kind of lets you grab images from the camera and then identify subjects in the frame, train the chip that way.
Cool.
Yeah, and we've that tool is especially good for just kind of like quick and dirty demos. You can get it to do face recognition pretty quickly that way.
Wow.
But it's not very robust. It's kind of quick and dirty. Yeah. So and I think at this point we've got some tools, but then we also just kind of support our customers on a per customer basis to give them the specific tools that they need. So I think hopefully, the dream is to have a really nice development environment that's really powerful and flexible and makes the training process easy.
Yeah, assuming that's better for you guys business-wise, and if consulting is basically,
Yeah, that's true.
You doing all this custom stuff for them, then interestingly that might be better to not make it as user-friendly.
Right.
You need us.
Yeah, I think at this point, since it's very different, it's a completely different paradigm to computing really. It's a chip that you train instead of program. So I think we're at the stage where we've got to convince people to work with it. Hopefully eventually we'll have people clamoring to use it. But no one makes sense. All right, yeah. So I'll get into this. And the interesting part is the machine learning and how we actually classify the hand. But just a few details on the first step is really to extract the hand from that depth frame. So I don't know if you guys noticed. Should have pointed it out, but in that Kinect utility in the corner there was kind of a grayscale image that you could see. That's the depth data being represented as just a grayscale image where the darker pixels are farther away from the camera and the lighter pixels are closer. So that's kind of how they visually represent it. And so we take the shape of your hand from that depth data, and the way we do that is we start by taking kind of just a square cutout around your hand, and we know where your hand is because the Kinect SDK gives us that information. That's part of the skeleton tracking input, which is great because that's probably one of the hardest parts of the problem is just locating where your hand is. So they've taken care of that. So so we start with a square window, and then the depth data, we're able to, every point in the depth data, we're able to translate into a 3D coordinate in meters. So we know it's X, Y, and Z coordinate relative to the Kinect sensor. So what we do is every pixel within that square window, we take its coordinate and we find the distance between that point and the point that the Kinect is identified as your hand. And any pixel that's within 6 inches of the hand, we say that's your hand and we keep that. And then anything that's farther than 6 inches, we filter out. So what that amounts to is what we kind of shot in this little picture is that you're kind of taking like a sphere, you're extracting a sphere around the person's hand with a 6-inch radius.
What were the names of the two algorithms that you optimized them? One was a near, one was a
K-nearest neighbor,
K-nearest neighbor,
and then Radial-basis function, RBN.
Okay, so I understand how, I'm guessing you're using K-nearest neighbor for this. Could you just describe it?
We're actually,
Or both?
for the extraction, we're not using any machine learning algorithm. It's just kind of it's sort of a threshold function.
Okay.
We say anything, any point that's 6 inches away from the hand, farther than 6 inches, we eliminate. And the purpose of that is to get rid of the background. So if I'm holding my hand out in front of my chest, we want to see just your hand. We don't want any background information confusing the recognition. Having background information makes the recognition a lot harder, so you've got to account for all the different possible backgrounds that can be there. So if we can eliminate the background, that makes the problem a lot easier. So here's actually some example images of what your hand looks like when we extract it. Yeah. So the other thing that's great is the depth data is light invariant. So it doesn't matter. You can actually use this in complete full darkness. So it doesn't matter how much light is on your hand. The infrared depth sensor is it's just measuring depth. So, and then that also means that you know, the color of your skin doesn't matter. You could be wearing a glove, that's all right. The color, texture, pattern, all that kind of stuff is eliminated. What we're left with is just kind of silhouette of the hand. That's a lot easier to recognize. The other factor that we kind of have to normalize for is the scale. So I could be standing really close to the Kinect, or I could be standing farther away. And depending on how far I am from the sensor, my hand's going to be the size of the frame. So that top image is from about 8 feet away from the sensor, and the other one's about 3 feet from the sensor. So you can see they're different sizes. So the way we deal with that, it's not too bad. We actually just prop in on the hand, the center, and then we scale all of the input hands down to a common size. So you can see at the end there, they're basically the same size now. So that eliminates the problem of scale. As far as rotation goes, we don't have any fancy tricks for that. We basically just have to train it on examples of hands and lots of rotations. All right, so that's how the extraction works. So now to the actual machine learning part. So right, so there's two algorithms in the chip implements, KNN and RBF. We actually use RBF to do classification in this demo. But I thought I'd walk us through how KNN works. KNN is a simpler is the simpler of the two algorithms. It's easier to understand. And then RBF is kind of, in a way, RBF is kind of built on top of it. So I think it makes sense to kind of go through this first. Let's see. So yeah. So so this is kind of how you might go about doing this demo with KNN. So one way you could, so you've got an input hand. You don't know what it is. You're trying to recognize whether it's an open hand or a closed fist. So one thing you could do is you could gather, like we've done, you could gather tons of images of people's open hands and tons of images of people's closed fists, and put them in two different directories. And then when this input hand comes in, you could go through every single one of those example images that you've categorized and compare it to each of those, and figure out which one it most closely resembles. And ideally, in this case, the image that it most closely resembles would be one of the open hand images. So you'd say, okay, this is an open hand. So you're finding, so that's what the nearest neighbor means. You've got a collection of labeled data points, and you want to find, for a given input, you want to find which point is closest, which data point is closest to your input. So which data point is its nearest neighbor. And then the K comes in from the fact that you could say, give me the top, let's say 5 results. Find me the 5 closest, and then I'll classify it as being whichever class is most represented in those 5. So you came back with the top 5 results were 3 open hands and 2 fists. And you would say, well, there's more open hands out of those 5, so I'm going to call it open. So that's what the is. Yeah.
Is there no kind of short circuit where you like look at the first view and open, look at the first view and closed? It looks way more similar to the open hand, so don't bother checking all 1,000 open hands and all closed hands. Like, is there anything like that?
No, yeah, you don't know. It could be that the open hand, it could be that it doesn't match. Let's say like the first examples in my database were all rotated in a completely different way. Okay. So it might not match any of the first ones at all. Yeah, so you've got to go through the whole data set.
Is the open hand also like open fingers? Like if somebody was like this, could it get confused for a, looks like it could get confused for a fist?
Yeah, we can try it. I think, there is, let's see, there's actually, sorry, I was tapping on a few slides. I think it would handle that pretty well. We've got a lot of training images that really look like a mitten, where your fingers are pretty much glued together. So yeah, it's pretty. What's great is that it's a kind of a fuzzy algorithm, because you're not saying that I want to find what this input matches exactly. You're just trying to find which it's closest to, so there's some tolerance there for some variability. So I think if I bet you could trick it if your thumb's not there. You know, if you do really like a flat hand, then yeah, I might have trouble with that. And actually, with we'll get to this, but there's a way to say, well, that hand doesn't look like either of these. I don't recognize that, so I'm not going to. So, oh yeah, so one of the things that I kind of glossed over in that description is that when I said, well, so take the input and compare it to each of these examples. So how do you compare it? What's the distance metric? And what we use for that is pretty simple. It's just image subtraction. So you take, so you've got input A and example B. So you take the corresponding pixels from A and B and subtract their RGB values and just accumulate all those differences. So it's kind of like laying two images on top of each other and subtracting the pixel values and taking the sum of all those differences. So you know, it's kind of a crude method of comparing two things because it obviously doesn't handle well. You know, if the image shifts, or like, as humans, we're able to kind of see like these are all the same thing. You know, we can tell that they're all open hands, even though they're rotated and things like that. So yeah, so the image subtraction is kind of a crude comparison metric, and we just have to account for that by using lots of examples of different rotations and positions. So any questions so far about Kinect? The next thing I'll do is explain. So you can see that I think something you alluded to is just that there's all these examples and you gotta go compare it against every one, and that kind of sucks. It doesn't scale well. The more examples you have, the longer it's going to take to classify input. So our chip solves that problem in a really cool way. So I had in the first slide, the chip has 1,024 processing elements in it, and the way it implements KNN is that each of these examples that you have in your database are loaded into one of those processing elements, one example per element. And then when an input comes in, you want to classify, it gets broadcast to all 1,000 of those processing elements in parallel on a parallel bus. And then each element independently computes the distance between the input and its model. And then the chip has a way of automatically sorting those results so that you get the top result or the top K results back in a fixed amount of time. It's independent of the number of examples stored in memory. And it's able to do that really fast. It does it in 10 microseconds. And it's designed to be scalable. So you've got this board just has one of the chips on it, but this guy has 4 of them. And it's kind of trivial to the way it's designed. It's trivial to just connect more of these in parallel. And you can actually like stack these boards vertically and horizontally. You have up to 1 million processing elements all connected together. And whether you have 100 of them working on it or 1 million, the recognition time, the response time is the same because they're all operating in parallel. So yeah, so it's pretty. Any questions about the chip? How the chip does the KNN process? Yeah.
Is there some benefit to making sure that K is a multiple of 1024 or anything like that? I'm just trying to think of any optimizations you could do.
Yeah, you know, in the applications I've done, I've always ended up just using a K of 1. You know, if you read about the algorithm online, the way to describe it is when you take a K value and you assign the category with the majority. In my experience, usually if you just go with the top result, that seems to perform pretty well. it may depend. I think one of the things KNN is good for is if you don't have that many data points for some reason. Maybe you're doing like one of the things that we've done is like a one-shot learning gesture challenge where you get one example of the gesture to train your chip on, and you got to recognize it after that. So KNN is good for that because you can say, I just need to know that I know that the gesture that's being performed matches one of these categories, so I just need to know which one it's closest to, and then pick that one. Yeah, so KNN, there's a couple problems with it. One is that with the hand extraction, we're using this 6-inch radius, and if the player's hand gets too close to their chest, we can't really distinguish their hand from their chest. And so what we get back is just kind of this blob. It's just an unrecognizable hand. Or the other thing that can happen is if you the skeleton tracking seems to fall apart if you kind of overextend yourself. If you like reach out to the side, and the hand joint starts to creep up your forearm, and so what we get is your forearm instead of your hand. So there's times where the hand that we get that we're trying to recognize is unrecognizable. We don't want to classify it. We don't want to because when we're doing the mouse control, what we do is if we recognize a fist, then we click the mouse button. If we recognize an open hand, then we release the mouse button. So we don't want any false positives on that. We don't want to miscategorize something as a click that we didn't intend to do. So we want a way to be able to say, well, this hand just it doesn't match closely enough to any of our examples, so ignore it. Just toss it. We don't operate on it. And KNN doesn't really have that. It's gonna tell you which. It's gonna do its best to classify it as either open hand or closed fist based on which one it's supposed to. There's no notion of this is unrecognizable. The other problem is that you've gathered 50,000 examples, and a lot of those are redundant or just very similar to each other, and they're not really adding that much knowledge to the database. So how do we figure out which of those we actually need? So with our chip, you could stack a whole lot of them together, and you could cover that 50,000 examples, but you could do it more efficiently if you could weed out the examples that are kind of redundant or too similar to each other. So so those are the two problems with KNN. So and I think you can kind of imagine some possible solutions to those problems that kind of listed on the slide here. So how could we distinguish a hand as just unrecognizable? So we could use a distance threshold where we could say the distance between the input and the closest matching example needs to be lower than 1,000, or it's just not close enough to match. That's the call it a match. So you could do kind of a global threshold like that, or you could take it a step further and you could say, well, there's some hand examples where it's like the fingers are really spread apart, it's really clear, and so it's really obvious that if it looks anything like that open hand, then it's probably an open hand. So we can use a higher threshold for that example. And then there's some where maybe your maybe you're like on your way to closing your fist, so your fingers are kind of clumped together a little bit, and it's not that clear that it's an open hand. So we want to use a smaller threshold for that, so that it needs to. We're not going to call that one an open hand unless it really closely matches the example that we have, since it's so close to the boundary of being an open hand or closed fist. So you could apply distance thresholds per example, and then as far as kind of filtering out redundant examples, we could say that we should only store examples that aren't already covered by the existing examples and thresholds that we have. So we've got one example in the knowledge base, and it's got a particular threshold, and then we look at the next example, and we see that it's already recognized by the existing example that we have. So we can leave that out. It's not giving us that much information. So those two kind of modifications to the algorithm are kind of the beginning of what RBF is. So So I think to illustrate that further, walk through an example of how you would actually train the systems of it. So with RBF, every processing element stores a model and then a category that's associated with that model, and then a threshold that's specific to that model that we use for deciding whether or not a given input matches that model. And then in that last column, I'm just going to show the distance between the input and models. So each row in this table represents a one processing element in our chip. So there's should be 1,000 of them. But, I'm just going to do a small example. So we've got 4 rows in there. So you start with an empty chip. Doesn't have any models stored, and we've got. We're going to go through our training examples. Order doesn't matter. So we've got this open hand image, and we're going to assign it to category 1. Say open hands are category 1. So the first thing the chip does is it tries to recognize that hand, and since it doesn't have any models stored in it, it doesn't recognize it. So if it doesn't recognize it in the training input, then it's going to create a new model for it. It's going to store it in its memory. It's going to assign the category that we trained it as. And then the threshold, since there's no other models in the database, it just uses a default large threshold. Our default threshold value is 16,000. So that's our first model that we've learned. And then there's a utility that we have that uses well here that I think may help illustrate it for you. It's kind of another way of thinking about it. So I'm just going to add a training point to this space that's category 1. So the data point's added, and it's a model is stored as a model, and that processing element has this threshold. We call it the influence field. So it has this space around the data point where any inputs in the space are going to be classified as category 1. So you may be wondering, so why is that a diamond? Why not a circle? It's got a radius. Why is it a circle? And the reason for that is that our chip uses a different equation for computing distance. The one that we learn in high school math is called Euclidean distance. You probably recognize that. You just take the difference between the coordinates, square up, and take the square root of that. And that gets you the straight line distance between 2 points in space. Our chip uses something called the L1 distance. So the Euclidean distance is the L2, and we use the L1. It's much simpler to compute. All you have to do is take the absolute value of the differences in the coordinates and add them together. And it's also called the Manhattan distance, or it's got a lot of names. It's called the Manhattan distance. It's called taxicab geometry. That's because it's basically the distance. It represents the distance that the taxicab has to travel in Manhattan because of the city blocks. So pretend this. So this is like some city blocks in Manhattan. You're trying to get from this point to this point. The green line is the straight line Euclidean distance. But the taxi cab has to stay on the streets, and so it has to go. Has to take more of a roundabout approach. And so each of these, the red, blue, and yellow lines are all the same distance. Correspond to this L1 distance. So this is 6 city blocks tall and 6 wide. So the L1 distance between these 2 points is 12. So you have to go up 6 and over 6. So you have to travel 12 blocks to get there. That's true regardless of which path you take. Whereas the Euclidean distance is the square root of 36 plus 36. So something like 8 point something. So if you look at, so this example, let's say each of these little squares is 1 unit. So all these red points are a distance of 2 from the origin if you use the L1 distance. So to get to here, you've got to go basically a circle with a radius of 2 looks like a diamond using the element distance measure. And the reason we do that is just that it's a lot easier to compute the element distance, and it's close enough for most applications. If you want to do the L2, you can see that there's a squaring operation in there, so you need a multiplier, and there's a square root as well. So it takes more hardware to implement the L2 distance.
Are you just using 2 dimensions or 3 for your L1 city for your distances?
So to illustrate here, it's just 2-dimensional because it's easier for us to think about. Our chip uses 256 byte vectors, so the inputs to the chip are actually 256 dimensions. So you look at the space represented by one of the models in the chip is actually a hypersphere because it's a sphere with 256 dimensions. So then with image data, each component of the vector is just 1 pixel. So so it's not maybe a better example of something with 256 dimensions would be maybe if you wanted to store someone's profile, so you've got like all these 256 properties of that person. So, okay, so we've got walking through our training example, so we've got one model trained in there. In order to train the next example, this one's a close miss. We're going to train that as category 2. So the first thing the chip does is try to recognize that input and basically compute the distances between the input and all the models. So we do the image subtraction, the difference between this image and this image is 9094. These are different categories. So we don't want this to be recognized as category 1. So we adjust the threshold of the first model to just exclude this training example. So we set the threshold to 9003. And then since our second training input isn't recognized correctly yet by the chip, we need to commit another processing element for it, store it as another model. This one's category 2 since it's a fist, and then the threshold value that we choose is chosen to just exclude the existing hand model. So the threshold there is also 90. Show that as well. So this equates to I'm going to add a training point now for category 2. The space of the first model, and watch what happens when I add this. And so the influence field, the first data point, shrinks to just barely exclude this green data point. And the green data point, the model is added for that, and its threshold is set to just barely exclude the red. So we keep going through all the examples. So here's the third input. This is another example of open hand. So we're training this category 1. So the first thing the chip does is compute the distance between that input and all the existing models. So the distance between the first model is 9,590. The second model is 16,000. So it's currently unrecognized. It's not being recognized as an open hand or a closed fist. So we need to add another model for it to recognize it, and we set the threshold to just exclude this existing this example. So we set the threshold to the distance value between the input and the outside of the influence fields of the existing models. So its threshold is set to just barely exclude that gradient. I think this is the last training. So we do one more, let's say, excuse me, another closed fist. This time, you can see that the distances that are computed, the distance versus the existing closed fist model that we have, it's within that model's threshold. So it's already being correctly recognized by the chip as a closed fist. So we don't actually commit another model for that game. So that's dealing with that problem that we brought up. We've got all these examples. How do you know which ones are actually important for creating the decision space, basically? So here we're saying we don't need to create a model for this input because we've already recognized it. So we've got about 50,000 examples of open hand and closed fists, and you go through this training process. It takes about 900 models to correctly classify every single input in the training data set. So that's the knowledge base that's running to do this demo. I think that's all I've got for slides. Some of the backup ones, but that's how RBF works. Any questions?
Yeah. So you said something like train as category. So you have to tell it, hey, I'm going to create a new category now. Don't expand the existing one. Don't try to augment category 1 is also including this next example. I'm creating a second category.
Right.
Yeah. So you have to just tell it that.
Yeah. So that's what makes it supervised learning. So every input that you show to the chip is already classified. You've classified it probably by hand. As belonging to a particular category.
I guess I'm a little confused by the third input, which is category 1, which has the default threshold at a very large distance. What's it comparing to?
Yeah, let's see. So it's not quite the default distance. It was a little less.
Okay.
So the threshold that we gave it is equal to the distance between that hand and the closest matching closed fist. So we pick the threshold to make sure that we just exclude the closed fist.
I see.
I think technically I should have made that the threshold should probably be 16,233. So it's one less than
so I see there's it's kind of, okay, I see kind of why it's category 1, but then why isn't it category 3? I guess is what I'm not really clear on.
Yeah, so the categories correspond to the classes that we're trying to recognize. So in this problem, we only have 2 classes.
Okay.
Open hand and closed fist. So everything is either category 1 or category 2. We could add in more hand gestures and label them as different categories. So if you want to do like a peace sign, I can make that category 3. Loose, category 4. Yeah, so the RBF is where the chip starts to take on some intelligence and it becomes, if you go to our website, you'll see we use the term hardware neural networks a lot. And I think that's, RBF is where it becomes kind of a neural network. Myself, I'm still trying to learn, I'm still learning about what an artificial neural network is and trying to understand the distinction between what are, in what ways our chip is a neural network and which ways it's not. I think there's some, I've seen in some of our slides that other people have presented, there's some important ways that it's not a neural network. Neural networks have some problems with they're like non-deterministic, right? And you can train them, and then they may not correctly classify your training inputs. Whereas our chip is RBF is kind of guaranteed to correctly categorize everything you train it on. So yeah, it's guaranteed, I guess, to converge on a system that correctly classifies all the training inputs.
Why didn't you correct for rotations? It seems like you could say, okay, you know, first finger is always pointing straight up in all of our examples or something. You just, and the subtraction would be much more accurate.
Yeah.
As opposed to this and this
Right.
being seen as like extremely different.
I think it's kind of a chicken and egg problem, because in order to correct for rotation, you kind of need to recognize like what orientation the hand is in. And then, then you could correct it and say, okay, well, that's a hand at 45 degrees, so I'm going to rotate it by 45 degrees to make it look
I guess you could go meta a little bit and then train some high level algorithm and like tell it that this
Yeah.
in all these examples the first finger is pointing up, and then that can make the machine learning algorithms that it is training smarter or something like that.
Yeah, I think you could like you could train it to recognize that this is a hand and this is a hand that's pointing in this direction.
Okay, right.
And then first try to recognize the orientation of the hand that way, correct the orientation, and then try to recognize whether it's what hand pose they're in right now.
But for your purposes, you don't need to need all the extra computation.
The great thing about the chip is that you can be, it's pretty, I don't remember if I said this earlier, but it's kind of a brute force approach, which normally brute force approaches aren't good because they don't scale well, they've got performance problems, but we kind of solve that with our chip by doing all the comparisons in parallel. So the neurons are cheap. It's easy to add more of them, and so to make the problem manageable, we do, if there's things that we can easily normalize for, then we'll do that. But in the end, we just fall back on taking advantage of the chip's strength and just using lots of models to do recognition.
Seems like there are definitely going to be times when you really can't tell which one it is, like during the transition. And so there is, in a sense, a third category, which is kind of neither one nor two. And it seems like you get there now sort of by default if it's neither one or two. Had you thought about actually having a third category, which was the in transition? And then if so, why did you decide to approach it the same?
I think the problem with trying to define a third category is that third category is kind of unbounded. It could be a screwed up hand could look like anything. There's infinite variability to what that could look like. So you can't cover it with a sufficient number of training examples to be able to distinguish that. So I can actually show you guys.
What you're saying makes sense to me as far as a screwed up hand can look like anything, but specifically the in between, then a hand that looks like both. You could say, oh, it's in a certain category, as opposed to a hand that looks like neither, in which case that is unbounded.
Right.
So it still seems like you could do what he mentioned.
Yeah. Let's see, what have I done with that? I've got, let me show you first. Pick it up and so we've got,
Cat on a branch.
yeah. Tell me what you see here.
Yeah, the ink flop for sure.
So yeah, so some of these bad inputs are pretty mild. It's not too bad. That's the hands. That's the use of yeah, and then there's you guys were mentioning. They did let's see. Yeah, transition. So these are all examples of that sort of out of frame, kind of on my way down to making a fist. And I'm not currently doing anything with these. I could train these as a third category, which sort of recognize that transitional state. But I'm not sure. I don't think I have any use for that currently. I think as long as it correctly categorizes a clearly open hand and correctly categorizes a clearly closed fist, I think that is sufficient for managing that mouse state transition.
And so does that mouse state transition just kind of activate on state changes of the hand? So like if it thinks it's closed and then it gets a lot of stuff it doesn't understand, it just stays closed?
Exactly, yeah. So it waits until it recognizes a hand of the opposite category to change the mouse points.
I guess you could also just do simple thresholding as far as they probably didn't just try to click 3 times in half a second or something and smooth things out that way.
Maybe a double click.
Well, yeah,
Yeah.
I'm wondering, what the maximum click frequency you want to allow for the kinds of purposes that you care about.
We played with that sound. I'm trying to remember where we landed. Yeah, it's not going to come to me while I'm sitting. We did something of that sort. We definitely played with like, well, no human can pull this off, 3 times in 1/10 of a second. So don't change state quicker than. So I'm not sure if that's the final approach that we use. So one of the demos that we show this with that's kind of fun is a game called Roll of Cube. The way you play it is well, actually, it's kind of a physics puzzler game, and I think it maps pretty well to this to what we've done here, because it involves you have these building blocks that you use to build towers, basically. It's kind of the game uses kind of a drag and drop mechanic. Get my screen resolution to match this TV exactly.
Have you guys played this before?
I saw the demo on YouTube. That's pretty cool.
This is a fun game.
So you wave your hand to take control of it. Is anybody wearing sleeves? Yeah, if you're wearing sleeves, you want to pull them up because it doesn't. Your cuff will screw up the recognition. And then it helps. The skeleton tracking works best if you keep your hand kind of away from your body. So if you notice that it starts to act weird, then you just kind of force yourself to push your hand out of the body. So clicking is a little awkward and kind of a quick closing. Some of these smaller buttons, it helps if you kind of hover over what you want to click on first. Drag and drop is a little easier. Fortunately, the game kind of has kind of this looseness to it where it will select an object as long as you're close to it. So the object of the game, there's always, every level has one of these pipes at the end. You're just trying to build a structure and reach the pipe. And then you try to do it basically using as few of these blue balls or building blocks as possible. And every level has like a minimum number. It's kind of like a par for the course, where you've got to, this one you've got to collect at least 4 blue balls at the end. If you want to stop using it and let go of the mouse control, you just cross your arms in front of your body, and that releases it. So try it, you're welcome to, or for the other stuff if you're interested. So, there you go.
Yeah, definitely.
You gonna do it?
So yes, so again, how is this using,
So start, raise your hands to grab it.
so above and beyond what the Kinect can just normally do?
Uh-huh.
What part is your chip doing? I think you said, you know, so this is like your chip simulated in software,
Yep.
some part of it?
Yep. So we're just doing we're just recognizing the open and closed hand.
Right, okay, and then you're just like telling the computer, like, you're
Yeah.
simulating some like input device, just like
Exactly,
click
yeah.
down now.
You simulate mouse events.
Okay.
Yeah. Oh, you picked like the hardest one.
Yeah, this is not an easy level. I'm gonna go back.
Rub your belly.
The menu button's like, it's kind of clipped in the bottom there.
Stuff.
So when you open your hand, try to do like a kind of exaggerated, yeah. And then the Kinect needs to like see your palm. So
Okay.
yeah, so make sure that your hand's like oriented in a way that the Kinect can see it.
It's kind of like,
Yeah,
Yeah.
I touched that. Yeah, this was hard for me to do on an iPhone.
Right.
I remember this level.
This one took me a few tries. The other game we demo that's a little easier is Angry Birds, but everyone does that one, so.
You're going nuts.
the whole thing just like flop off the edge.
Yeah, I feel like they're gonna sink in the swamp. Walls. You have to kind of like hold your hand like palm away from you for it to see what your hand was. Okay.
Yeah.
Because right now it's probably seeing more of like a karate chop. Might actually get it.
I'm surprised I haven't died yet. Talking this.
So another question about your chip.
Yeah.
I'm wondering if when it like recognizes things, especially in the human body, if there's any areas that it's kind of better at. Like right now, it's recognizing the hand, but you know, it's like it could recognize lips or no. I mean, it's so. Are there certain parts of the body that it's better at?
Yeah, you mentioned like the resolution not being good enough for small hands. Is there?
Mm-hmm. Yeah. On the, I mean, that's the resolution on the Kinect sensor. That's the limitation there.
Right.
Do you know, like could it like just as easily see which way my head is rotating as you know looking as the hand, or if my eyes are closed, or
Yeah, I think you know, with your eyes and your lips, I think that would be you'd want to do that more with like the RGB data. You know, you would need to see, I guess, the the changes, and you need to see like the texture of the face and
Right.
the change in color between the lips and your skin, that kind of thing. So I think the depth data is a little easier because the hand, it's easy to recognize the shape, which is kind of this distinct
Right.
silhouette that you're looking for. Yeah, and then head tracking, they actually, Microsoft supports head tracking with their, wow, I'm impressed.
That actually works amazingly well. The difficulty we're seeing was not the classifier, was just me not knowing how to do this. I'm one short.
Oh man, is there one on the right there? There's like, I think I saw one, a live one on the very far right that's like clipped from the screen.
Like down here?
No. There you go. Yeah, there you go. That one's live.
Oh, I can grab it?
I think so.
Oh.
There you go. Nice.
Us.
On your first try too, that was impressive. Yeah, and if you need to reach like one edge of the screen, you can definitely like, you know, sidestep. It's like I mentioned, if you try to like stretch, then the Kinect kind of does a bad job of finding your hand.
It'll get confused.
Yeah.
That is amazing.
Cool.
Anybody else want to try this?
Sure.
So how does yours compare? I mean, there's other like there's sign language recognition software out there now, right? So it's gotta be-
Using Kinect or like OpenCV maybe?
I have no idea. I mean, pretty sure there's a couple of them out there. But
Yeah.
how do they compare in terms? I mean, they've got to be using essentially a very similar algorithm what you guys are doing.
Yeah, not necessarily. But yeah. We picked this one more because it's what our chip does,
Right.
as opposed to,
Mm-hmm.
experimenting with different algorithms and finding the best one.
Mm-hmm.
Microsoft has proven that RDF works, really well for this stuff.
Nice.
So I think if we had our choice of algorithm, we'd probably go with that one.
The red things are balloons.
This is another really hard one.
This is really hard. I don't think I ever got past this one.
Really?
Okay, I never played this before. I don't like my chances. So how do I?
But not too high because it'll pop.
Oh, I see.
Not too low either because it'll pop.
Okay. So there's this.
And you gotta reach in there just at the right split of a second.
Yeah, so when it like,
Who'd have thought of this game? I've never seen that.
So how do I get to? Okay, I unclenched it.
yeah, you only want to let go when you see those white lines. That means you can place a goo ball there.
Oh, okay. I get you.
Yeah, I think we could do sign language with this. One tricky part is we looked at doing the alphabet, and there's some letters in there. I don't know sign language. But there's some where it's like you make a fist and then you put your thumb in a specific spot.
Oh,
Yes.
right.
Yeah, it's
like
Eminem,
That's a great
yeah.
idea.
S, like S versus A. Like
Yeah.
S is like when you have this in front, A is like that. That's
Yeah.
kind of hard.
So
And are there any letters where you actually have to move your hand to like complete the letter, or is that just
maybe J.
Yeah, I think
J is like that?
Yeah, like what you just did.
Huh.
Yeah, and then I think a lot of the words I think use movement, right? So
And this was featured on Hack-A-Day, right?
Yeah.
Oh, that's awesome.
That's fun.
Well, another thing I saw on Hack-A-Day which related to hands was a robot that you play rock, paper, scissors with.
Oh,
and it would figure out what
beat
you would play. Yeah, like
Right.
it would determine like in milliseconds what you would play, and it would figure out like it would beat
It
you
would cheat
basically.
really, really effectively.
Yeah.
Yeah, that was cool.
Oh, so as you begin your move, it reads it and says, oh, he's
Yeah.
doing this.
Yeah, he's playing rock, so I'm gonna do paper. And it's actually like a robot hand, so.
It's really loud, right? The robot hands like.
I never saw the video.
So what do you think are some of the things, the really interesting things about machine learning and stuff like that? Things going on.
I'm in it for. I want to see like cars that drive themselves and personal robots, you know, that do everything. That's kind of. I feel like those are the two like holy grails of machine learning. And I think and I guess something I've learned as I've been trying to learn more about the field is that there's definitely different aspects to it. I think what our chip does, you would call classification, where you're using machine learning to try and recognize an input as being something.
Right.
But then there's other fields within machine learning that I think may even be more common. There's one area is called regression, and it's where you've got a collection of data, and you want to fit a mathematical model to that data, and then once you have that model, you can kind of predict future values of the data based on arbitrary inputs. So like the stock market prediction or something.
I was looking around for machine learning stuff. It's hard to find someone who's not building a recommendation engine, basically.
Yeah.
Like, here's all the things you like, so there's the
Yeah.
training set, and then here's all the things you might want.
Right. I mean, I think another area, I'm not sure if this is distinct from those other two, but clustering. There's a concept called clustering where you're trying to, you've got a bunch of data and it's not labeled, you haven't categorized it, and you're trying to discover some categories basically in that data.
Right.
So like if you've got maybe the typical example is like you've got customer information and you're trying to recognize patterns in your customer data. So it's so it's been interesting to learn that machine learning isn't just getting robots to be intelligent. There's these other applications. It seems to me what defines it is like anything where you're using example data points to configure the parameters in some kind of equation or system. So anything where you're using training data as opposed to analytically trying to create an algorithm.
When I learned about like k-means clustering, I was like, well, I don't want to choose the k. I want you to choose the k, like find how many clusters there actually are, like not this artificial number that I came up with.
Right.
So yeah, it'd be interesting to learn what